Hello, bonjour, salamatibé, dobry den. Welcome to the 6th tutorial of Statistical Mechanics, Algorithms and Computations from the Physics Department of École normale supérieure. In this week's lecture and homework, action was all about the Levy quantum path, one-dimensional geometrical objects that are easy to sample, yet that carry a profound message. They lend a geometrical interpretation to the Heisenberg uncertainty principle. At high temperature and high energy, a particle is at position x with probability ρ of x beta. The quantum paths connecting x to x have no fluctuations, and the particle is really located at x. Likewise, the density matrix has no off-diagonal parts. In contrast, at low temperature, the particle is uncertain in its position x, as the quantum path fluctuates wildly from x to x for beta being large. This is also mirrored in the large off-diagonal part of the density matrix. In this tutorial, we touch on the second pillar of quantum statistical mechanics besides the Heisenberg uncertainty principle, namely the indistinguishability of particles, in our case bosons. For our introduction this week and the next week, we will concentrate on the case of non-interacting ideal bosons. This is not really a restriction, because non-interacting bosons are the only system in all of physics that have a phase transition without interactions. In fact, a curious statistical interaction appears in the system of indistinguishable bosons, and Michael and Alberto will trace it down in this week's tutorial. Unfortunately, Vivien cannot be with us for a couple of weeks, but he'll come back for our discussion of classical spin systems. We will put our ideal bosons into a harmonic trap, and this same system has set the stage for groundbreaking experiments in atomic physics, where Bose-Einstein condensation has led to a revolution in experimental glass cells just like this one. We will follow this revolution. You will follow these groundbreaking experiments in your own path integral Monte Carlo calculation using the path integral picture. But before doing this, Michael and Alberto will discuss Bose-Einstein condensation using wave functions and energy level. This is necessary in order to understand what it is all about, the Bose-Einstein condensation into the ground state. They will then discuss all of this in a simple model of a few trapped bosons.
Before putting many particles into a three-dimensional trap, let us first consider a single particle. This means we enumerate all single particle states with a given energy E. In 3 dimensions, a harmonic trap has 3 spring constants, one in x, one in y, and one in z direction, as is shown in the picture here. Just like in last week, we set all the spring constants omega x, omega y, omega z equal to 1, so that the energies Ex, Ey, Ez satisfy or are equal to 0, 1, 2, 3, 4, and so on. For simplicity, we set the ground level energy equal to 0 and label all the states by the energy Ex, Ey, and Ez, so that they have the total energy E equals Ex plus Ey plus Ez. Let us now write a little program, naive single particle.py, to enumerate all these states. Output of the program is shown here. For example, here we have state 12. It is in the ground state in X, in the second excited state in Y, and in the first excited state in Z. There are many states, but notice that each tuple Ex, Ey, Ez corresponds to a unique single particle quantum state of energy E equals Ex plus Ey plus Ez. Let's have a look at them. There's one ground state of energy 0. There are 3 states of energy 1. There are 6 states of energy 2. 10 states of energy 3. 15 states of energy 4. And so on and so on. Do you see a pattern? So let us now compute the number of choices Ex, Ey, Ez that give an energy E. For a harmonic trap, the number of states with a given energy E can be calculated explicitly, as is shown here. This expression means that for each choice of Ex, we can choose Ey as an integer between 0 and E minus Ex. Given Ex and Ey, then the remainder Ez is fixed. This means for each choice of Ex, we have E minus Ex plus 1 choices for Ey. And this makes that we have E plus 1 plus E minus 1 plus E minus 2 and so on plus 1 choices. In total, this makes E plus 2 times E plus 1 over 2 choices. This corresponds to 1 choice for E equals 0, 3 choices for E equals to 1, 6 choices for E equals to 2, and so on and so on. But let us now use a more systematic method to compute the number of states with an energy E. Alberto will soon use it in a more involved context. The method consists in writing the number of states as the free sum over Ex, Ey, and Ez, with the condition that we implement by means of a Kronecker delta function. We simply sum up the states, as is shown in this equation here, where the Kronecker delta is defined as is shown here. Because of the Kronecker delta function, only combinations of Ex, Ey, Ez that sum up to E contribute to the number of states. We can represent the Kronecker delta function by this integral. We can then enter this integral representation of the Kronecker delta function into the above sum. We then exchange sums and integrals. Then we see that the sums have become independent, as is shown here. These are geometric sums that can be evaluated explicitly, as you see here. Finally, we can evaluate the remaining integral using brute force Riemann integration, as Alberto will demonstrate in a few minutes. This numerical integration is all that we will need here. But those of you who feel at home in the complex plane know, of course, that this integral can also be evaluated exactly. The substitution e to the I lambda equals z leads to a complex contour integral that can be evaluated using the residue theorem. And of course, the result is e plus 2 times e plus 1 over 2. Now, let us do 2 things. First, in our list of single particle states, shown right here, let us retain only the 35 states of lowest energies. That is, the states that have energies smaller or equal to 4. We now have a list of 35 states, and we can still look at them here on the screen. Second thing, we now put 5 bosons into these states. Remember that the partition function of a physical system is equal to the sum over all states of the probabilities of each state. And this probability is given by the Boltzmann weight e to the minus beta e. The partition function of our 5 boson system is then put together from all the different ways we have to put the 5 bosons into the single particle states. For example, we might put our red particle into this state here, the blue particle into this state here, the yellow particle into this state here, the green particle into the state here, and finally the pink particle into the state here. The sum of all these possibilities is the partition function, something we can measure. And while we should be careful not to forget any of the 5 particle states in our partition function, we are not allowed to overcount them either. The problem arises because bosons are identical particles. They don't just look the same, they are indistinguishable, and there is no way to tell them apart. These 3 states here are different for particles that are distinguishable, for example, by their color, but for bosons they are one and the same. In our partition function, we should count only one of them. This is one of the most profound insights in all of physics. It is due to Bose in 1923 for photons and Einstein in 1924 for massive bosons. We can translate this great achievement of Bose and Einstein into a simple algorithm. In order to avoid overcounting many particle states, we count only states that satisfy that the single particle state of particle 0 is smaller or equal to the state of particle 1, is smaller or equal to the state of particle 2, is smaller or equal to the state of particle 3, is smaller or equal to the state of particle 4. Out of our 3 states, we thus pick the last one. The other 2 have to be dropped from our partition function. Alberto will now leave this graphical discussion and put our 5 boson model with its 35 states onto the computer. But before doing so, please take a moment or two to go over our discussion of single particle states and 5 particle states, and to download and to run our nice little program naive singleparticle.py that helped us to create this nice list of states that we are discussing all along.
The ordering trick that was introduced by Michael allows us to compute the bosonic partition function with distinguishable particle. Remember, you put the particle 0 in a state between 0 and 34. Then you put the particle 1 in a state between the state of the particle 0 and 34. Then you put the particle 2 between the state of the particle 1 and 34, and so on. This 5-particle state has an energy E given by this formula, and a statistical weight exponential minus beta E. This allows us to write the bosonic partition function as follows. But maybe you prefer to see this as an algorithm. Note the curious line. The multiplication of a list with an integer factor k simply concatenates the list k times, so that 1 times 3 is simply 1, 1, 1. Here we compute the partition function. The multiple loops are really naive, but we can compute the number of states which contribute to the partition function. It is a large number, 5, 7, 5, 7, 5, 7, but it is 90 times smaller than the number of states for distinguishable particles, which is 35 power 5. Can we compute this number? Of course. Let's look again at the bosonic states and erase all information on them. We have 35 boxes, which means 34 inner walls. We can now put the 5 bosons inside the boxes. The number of states corresponds on counting how we can arrange 34 plus 5 walls and boson, taking into account that walls as well bosons are indistinguishable. The number 575757 is then 39 factorials divided 5 factorials divided 34 factorials. We can easily extend the program naive boson trap.py, counting the number of particles that are in the ground state. In this state we have 0 particle in the ground state. Here we have 3 particles in the ground state, and here we have 1 particle in the ground state. We can implement this in naive boson trap.py using the count of zeros in the least state. We can compute the average number n0 and the condensate fraction. Considerably larger number of particles and states can be achieved if we introduce the occupation number associated to a single particle state. In our scheme of 35 states, instead of drawing colored particle, we just indicate that the state 0 is occupied by n0 particles, the state 1 is occupied by n1 boson, and so on. So for example, this state can be written with these occupation numbers, and the energy associated to this state, actually the energy associated to any state, can be written as follows. The partition function of the system writes as follows. This expression is equivalent to what we have computed in naive boson trap.py. But it is even more complicated. Instead of the 575757 states, here we have 6 power 35 terms. However, now we have a bunch of sum and a delta constraint. Does this ring a bell with you? This is exactly what was considered by Michael 10 minutes ago. So we can use his providential representation of the Kronecker delta function. Note, the sums are geometrical sums, so that we can compute them. And of course, each sum depends only on the energy of the state and not anymore on the occupation number. We have to think 2 minutes to understand if we have to consider the finite geometrical sum or the infinite geometrical sum. And this is also done in the fact sheet that is associated with this tutorial. In any case, we can now arrive to an expression of the partition function, which is a simple one-dimensional integral over the variable lambda. This expression for the partition function allows us to compute all thermodynamic quantities, as the mean energy or the condensate fraction, which is shown here. We can compute this integral numerically using a simple discretization, and moreover, the cutoff of the energy Emax, which was fixed to 4, can now be increased as much as we like, and we can also increase the number of particles. For n equal to 5 and E max equal to 4, we recover exactly the same results as in naive boson trap.pi. Here we show the plot of the condensate fraction as a function of the rescaled temperature for a system of n bosons in an harmonic trap. Here we see that all particles are in the ground state at very low temperature. This is a simple consequence of Boltzmann statistics. At zero temperature, all the particles populate the ground state. The Bose-Einstein condensation is something else. It means that a finite fraction of the system is in the ground state for temperatures which are much higher than the gap between the ground state and the first excited state, which is 1 in our system. You see here that this fraction goes to 0 for a rescaled temperature T over n power 1/3 equal to 1. This means that the critical temperature of the Bose-Einstein condensation grows like n power 1/3 for an harmonic trap. This is a much higher temperature than 1 for large system. Clearly, this observation can be confirmed by explicit calculation, so you can really believe us when I say that the critical temperature grows like n power 1/3 for an harmonic trap. Finally, take a moment to download, run and modify naive boson trap.pi that studied the bosonic statistics and the Bose-Einstein condensation for a problem of 5 bosons that was really too small, but we came up with some idea, actually a one-dimensional integration that allowed us to go much farther.
In conclusion, in this tutorial 6 of Statistical Mechanics, Algorithms and Computations, we made our first step in the study of quantum indiscernibility, the second pillar of quantum statistical mechanics, next to the Heisenberg uncertainty principle. 5 bosons in a trap allowed us to shed light on the very essence of quantum statistics. This same model also allowed us to understand something about Bose-Einstein condensation, when all of a sudden a finite fraction of particles populate the single particle ground state. In a trap, this happens at higher and higher temperatures as we increase the particle number. Next week, we will take up the study of bosons and Bose-Einstein condensation in the language of density matrices and path integrals. And you will produce your own path integral Monte Carlo calculation to produce Bose-Einstein condensation in situation very similar to the experimental one that takes place in these glass cells. So, in the meantime, have fun with homework session 6 and see you again next week in session 7 of Statistical Mechanics, Algorithms and Computations for a study of Bose-Einstein condensation.